Okay, so in this video we take a look at how we might apply projectile motion equations to a serve in the game of tennis. Full disclosure, I am a lifelong recreational tennis player, so when I read this question I found it somewhat intriguing but also a bit limited in its scope and actual application to the game of tennis. Let's read the question. I'll explain what I mean. At serve, a tennis player aims to hit the ball horizontally. What minimum speed is required for the ball to clear the 0.9 meter high net? It's about 15 meters from the server if the ball is launched from a height of 2.5 meters. I'm going to stop there because if you've ever played the game of tennis, you know that there's some problems already. A tennis player doesn't aim to hit the ball horizontally. Most tennis players, like myself, aims to hit the ball as hard as they possibly can and then adjust the angle so that the ball can get over the net but still stay within the service area. So it's much more a question of what angle to hit that ball. And that again depends largely on your service speed. The faster you can hit that ball, the less angle you have to play with. So I looked at this question, I said, I want to change it. I want to consider what angle would be allowed or what range of angles would be allowed to have that ball get over the net and still in the service area. I first considered a professional level serve, 150 miles per hour, because I was interested to see just how challenging it is for them to be able to get that ball in that service area. Now when I went through and did that problem, it wasn't too bad. I just had to find a couple of angles that would allow that ball to stay in. But then I realized that the much better solution is to come up with a variable solution, one that would allow for any serve speed, any serve height. And so this video is going to show you that. Let's go ahead and take a look at it. I adjusted the question, much more of a level 3 type question, that for a given serve speed and serve height, determine the range of service angle for good serves. We're going to, again, assume the ball travels as a freely falling projectile, no air resistance, and no spin. The first thing I did is I looked at this diagram and said, well, I want to use variables throughout so that I can come up with a generic solution. So I updated the diagram to include these kinds of things. Instead of the given values of 2.5 meters and 15 meters and 7, the 15 and 7 meters are going to be standard for a tennis court, but the 2.5 meters would certainly vary, as well with the velocity. So I just used symbols throughout, and down here you can see what I'm using to describe this process up here. Critical things here is that the serve speed v is something that I'm going to sort of adjust to see the impact of it. And the other thing is I'm going to try to solve for theta n and theta s, where theta n represents the angle that would just allow the ball to get over that net, and theta s would be the angle that would keep the ball from going outside of the service area. Now what I did not show here was the velocity vector, and let's go ahead and draw that in here. Use a little arrow for this. So depending on what angle they choose to hit that ball, if they go with a shallow angle, that might be the one that would take it and get it right to that service line. If they make the angle a little bit steeper, that might be the one that just clears the top of the net. So really what I'm interested in here is what is the range of angles that will allow that to stay within that service area. Now the strategy for this is the same kind of strategy you always use for projectile motion problems. Consider x and y motion independently and then link them through the time variable. For this particular problem, I'm going to develop an expression for time based on the x motion and then use that expression for the y motion equation and then solve for the angle. And again, I'm either going to solve for theta n or theta s, and I'm going to do that with variables throughout. So let's go ahead and begin. First, we're going to solve for theta n. That angle would be the maximum angle from the horizontal that would just clear the top of that net. Now we're going to consider again time in the x direction first. So x motion is constant velocity motion. There's no acceleration that way. I'm going to rely on this equation to develop that expression for time. Now it's always important to identify the time interval. So step 2 here, the time interval is going to be from the serve, right when the ball leaves the racket, until it gets to the top of the net. Again, that's the critical point. We're trying to determine what angle would allow us to just get to the top of the net. So let's stop the time at that point and then develop an expression for that time and then plug that into the y equation to see where that leads. Number 3, I have some givens. Delta x is n for our given problem. V naught x is just v times the cosine of whatever angle it is that we eventually find. A sub x is 0, so there's no acceleration that way. Now the expression for time is rather easily done using this equation. Just solve that for t sub x. It's just going to be n divided by the speed at which it's moving in that direction. So n over v cosine theta n. Quite easily done. Now for the y direction, we're going to consider that y is freely falling accelerated motion, the equation that we're going to use is the same equation that we have here. We just have some different accelerations and some different initial velocities. We're going to use the same time interval that we developed over here. That way we can use the expression for time in this equation. Givens are a little bit different. Delta y is L minus h. When the ball leaves the racket, it's at a height h, and it's just got to get over the net there, so we're going to assume that it's right at the top of the net. The change in position would be L minus h here. Notice that is negative. V naught y is also negative because we're going to assume the ball is hit slightly downward below the horizontal. The acceleration is in the downward direction at a value we call g. Now, as we go through the equation development, we just plug in these values for our given into this equation. We get L minus h is equal to negative v sine theta. And instead of using time, I'm just going to use the expression that we had for time over here, n over v cosine theta n, and then plus 1/2 negative g, and then that's t squared. Now, this equation is somewhat involved, and my goal is to try to come up with a value for theta n that would allow me to hit that ball over that net. So I'm going to go ahead and modify this equation first by simplifying it. I see that that v and that v cancel out. Sine over cosine is a tangent. And let's see, I'm going to clean this expression up over here as well, and we get something like this. To solve something like this is really challenging. So what I'm going to do is I'm going to set it equal to 0 and then graph it to come up with a value for theta that will satisfy that. So when I go through and rearrange this equation algebraically, I get g times n squared all over 2v squared cosine squared theta n plus n tangent theta plus L minus h is equal to 0. Again, just follow through that math and you can see that that's the way that it works. Let's go ahead and open up a Desmos screen. And now what I'm going to do is I'm just going to plug that equation in here. Y is equal to...
We said g times n squared divided by 2v squared cosine squared x. Now we said that was plus then, that was n tangent of x, and then plus L minus h.
Because we're using variables here, we need to tell Desmos what we want these symbols to be. So g is the acceleration due to gravity.
Let's go ahead and assume we're on Earth. 9.8. N was the distance to the net, and for our example, that was 15 meters. L, let's do that one next. L was the height of the net, and let's see, that was 0.9. H was the server height, where they could hit the ball from, and so that was about 2.5 meters for that problem.
And B, let's go ahead and do the solution that I originally did with the professional tennis serve. 150 miles per hour is about 67 meters per second. Now, before we go any further, Desmos defaults to radians for the angle, so let's put that to degree, and it's a little bit easier for us to interpret. And here's our solution. Again, the 0, because I set that expression on the other page equal to 0 and then solve that, the solution here is showing me that at an angle of 5.152 degrees below the horizontal, the ball would just be at that net. And so that represents the angle below the horizontal for a successful serve just to clear the top of the net. Now my goal is to figure out the range of angles. So now what I need to do is I need to go back to my original set of equations here and then solve for theta s. Some key differences between our other solution is we're just going to replace theta sub n with theta sub s. Also some differences, the time interval is now going to be from the serve to the good serve line, so we're not going to consider the ball at this point. We're going to let the ball go all the way down here, and so that's going to change a few things from our solutions over here. Delta x is now n plus s. We have to add that length here to the displacement. The time interval increases because we're going to be in the air a little bit longer. The other thing that changes is delta y is now negative h. We're going to allow the ball to go all the way from the height of the serve all the way down to the ground. Now when we go through and do the solution, we're going to do the exact same process that we did over here. We're going to start looking at the motion in the x direction, develop an expression for time, use that value over here to be able to compute this final equation. And when you do that, you get something that looks very similar. The only difference is that instead of n, we have n plus s, same thing there, and instead of plus L minus h, we just have negative h. So exact same solution. We went through a lot of effort to be able to develop that here, quite easily done just by considering some new given information. Let's go ahead and take this over to Desmos and see what the solution is for theta sub s. So first we plug in our equation. Y is equal to
g times n plus s squared divided by 2v squared cosine squared x plus n plus s as a tangent of x. and then minus h.
We did introduce a new quantity called s, and so let's go ahead and define that here. That was the distance between the net and the service line on the other side. That was 7. And sure enough, when we put that in here, we get a new graph that popped up. Let's go ahead and zoom in, see what this tells us. So again, as I solved this problem initially, I was looking for just how difficult it is for a professional tennis player to get that ball into the service area. So it's got to get over the net and within the service line. And you can see now just how challenging that actually is for these professional tennis players. Now, again, 150 miles per hour is a world record serve speed, and 2.5 meters is not quite as tall as most people are that are professional tennis players. But nonetheless, this gives you a sense of just what kind of challenge exists to hit that ball super fast over that net. 5.152 degrees and the ball just clears the net. 5.11 degrees and the ball goes out of the service area. So they have very little room to play with there. There's that 0.042 degrees. So almost seemingly impossible. Now let's go over here and see if we change the height to something a little bit more realistic for professional tennis players. Maybe 2.9 seems more likely. Or we can see that increases the angle at which they can hit that ball below the horizontal. That makes sense. But what's really important here is the range of angles that increased height sort of provides. So instead of it being 0.042 degrees for a range of angles, this is quite a bit better. What is that? That's at least, it looks like it's over half a degree. Doesn't seem like much, but compared to 0.042, that's quite an advantage hitting that ball from a higher elevation. Now, I originally did this problem also to determine how easy it is for me to be able to hit that ball over the net. I can't hit anywhere close to 150, maybe not even 100. I'm probably more like 70 to 80 on a good day. So let's go ahead and put it in as 35 meters per second. A little bit shorter than the average pro tennis player, so I'm going to put that in as about 2.7, and let's just see where that is. Zoom out so I can find my graphs here. Okay, over here, and let's see, 3.42 degrees down to 1.983 degrees, so 1.4, 1.5 degrees almost. Again, not a lot of room for error, but considering comparing that to the professional tennis players, quite a bit easier job for me to be able to hit that over. Some other things that we can do. I can do a little bit of animation here. Let's go ahead and do that. Let's put in a value of, let's say 25 meters per second up to 55 meters per second. And let's just play this and see what Desmos can do for us. So we can see certainly the impact that serve speed has on the service angle, and certainly the faster you serve it, the shallower that angle difference is, or the smaller that difference in angles is, and the slower you serve it, the more room you have to play with. So something interesting going on over here. I see that we have some negative angles here, and if you remember how we devised this equation, we said that we were going to assume they're hitting it downward below the horizontal. So all this means here is that they would have to hit it above the horizontal, and that makes sense for slower speeds. They're going to have to angle the ball upward a little bit to make sure it gets over the net. And one last thing I want to do before we finish is I want to put this back to our original speed. Let's put this down at 67 and a height of 2.5. And let's see what that looks like. Yep, that's where we had initially. And what I want to do is I want to try to simulate, just to see if we can do this, maybe the effect of topspin. Going back to here, oftentimes if you watch professional tennis players serve the ball, they often hit the ball with a sort of a slight upward motion of their racket to try to impart some topspin on that ball. And the effect of that is to try to use a little bit of what's called Bernoulli effect to produce a downward force from the air itself that can sort of allow that ball to curve at a greater rate than it would just from gravitational force alone. So we might be able to simulate that down here by maybe affecting the value of g. Now we're certainly not going to be changing the local value of the acceleration due to gravity, but producing an additional downward force is going to make it curve more sharply. So let's go ahead and see what that would look like if we bring this back over to Desmos and just affect the value of g. I'm going to allow that value of g to range from 9.8 to, I have no idea how big we should artificially inflate this to account for topspin, but let's just put in something like 12 and let's just see what that does. So we can see that the more topspin we put on that ball, if we can simulate that by having g be at least artificially inflated to show a little bit greater downward force than just the weight, you can see that certainly does have the effect of increasing the range of angles that the player can sort of hit that ball and still have it be successful. And so if I just go over here, say that they have some topspin in there, what is it, 4.823 to 4.956, 0.13-ish, compared to 0.042. That's still significantly improved. And so perhaps we can use this simulation and this equation that we developed to try to see what the effect of topspin is on that ball. So there we go. That completes the video on projectile motion applied to a tennis serve.